Greetings, the Astro 30 here yet again, and I'm messing around with this older Amplifier DC protector circuit that I designed well back for that bass amplifier that I built, I don't know, 10-12 years ago now. And it's loosely based on a silicon chip magazine design which was around about 1996 for a loudspeaker protector circuit. Up here we have two diodes here forming a full wave rectifier with a ground connection or center connection. Light filtering with a 47 microfarad 63 volt. Going into this amplified Xenodiode shunt regulator, for want of a better term, comprised of a BD139 pass transistor, 4K 71 watt biasing and current limiting resistor, and in this version it was actually a 15 volt Xeno. I'm going to change this to probably a 13 volt or even a 12 volt, because using this type of circuit we're going to have a loss of about 0.7 of a volt. So that's neither here nor there. That circuit doesn't actually exist on my breadboard at the moment. I know this circuit works, but I've breadboarded it up again because I wanted to make a few little changes. And one of them in particular was this delay turn-on circuit here, comprising of this 240k to 220 microfarad capacitor. One, I wanted the delay to be around about 4 seconds. And this was originally 330k, and that put it out to about 6-7 seconds, which is a little bit long. And I also wanted this capacitor to bleed off its charge quicker than it was. So if the power was interrupted and it was reconnected, say 10 seconds later, well, you still have like a 2-3 second delay there. So I've added this extra 22k bleed resistor in here. The rest of the circuit is the same as it originally was. We're going through this transistor, which forms part of the tech network for DC, which also, when there's this is biased on, allows collector current to flow through here into the driver transistor, which is a PMP, which drives our relay. The other change I made was I used something that Rod Elliott discussed in his relays article, where you can get a faster release time on a relay by using not just a standard snubber diode like this going to ground, but we put this 24 volt Xenodiode in series with it, but in reverse conduction. And what this will do is when the relay drops out, it'll put the supply voltage, which the relay is 12 volt, the supply voltage is 12 volt, up to double. So there'll be 24 volts back EMF coming back through this transistor, which this transistor should be able to handle just fine. I will have to verify that this circuit works. Why would I use this? Well, you'd really want the fastest turn-off time possible so that DC doesn't make it to the speaker for too long. Like, if it was a, say, 40 volt supply rail that's going out as DC to the speaker coil may be able to sustain that DC voltage potential for 2 to 3 seconds before it destroys the coil. So if this can turn out within 100 milliseconds of the DC being detected, then anything you can do here to make it drop out as fast as possible is very important. And I will link in the description below that article that Rod Elliott wrote about relays, if anyone's interested in reading his thoughts on that. Now, we've got this other LED over here, which is our mute or protect LED, and what happens is this will flash when this circuit is not energized. As soon as this circuit is energized, well, it biases this transistor on, which then steals the supply voltage to that LED. And this 1K resistor here between the positive rail, which is here, and here, just prevents, well, basically shorting the supply out. So we're going to have some current draw across this 1K resistor all the time when the circuit's operational. So it is what it is. And down here is our detector circuit. Now I'm only going to show one because there's another circuit joined below to this point. So the way this circuit works is, say for instance we've got a positive DC potential coming in. Well, after this RC network reaches about 0.6 of a volt, this transistor over here, which is an NPN, is going to be turned on because it's an NPN transistor requires a positive base current in order to turn on. So the positive going DC cycle will turn this transistor on, which will then switch ground up, turning this transistor on, and then this delay transistor, which is the detect transistor, via this 10 ohm resistor. What that will do is then steal the base current for this transistor, discharging this delay capacitor and dropping the relay out. And conversely, if we have a negative DC potential coming in, well, that's going to travel through this emitter collector junction of this transistor, because this is turned on all the time because it's connected to ground. So from its perspective, it's getting a positive base current. They'll then turn this PNP transistor on, which will conversely switch up ground or switch down ground through the transistor via the 10 ohm resistor, removing base drive current to this transistor, discharging this capacitor, etc., and dropping the relay out. I've also provided an option for a thermal switch, which is normally open, which can be connected to the heatsink, say on 160 degrees Celsius thermal switch, normally open. As soon as that 160 degree potential is reached, the switch will close. That'll switch ground up into this off network, for want of a better term. So in case of a thermal overload, again, the base current to this transistor is removed, stolen. The transistor turns off, therefore the driver transistor turns off, and then the relay drops out. So it performs two functions. Not only does it detect for DC, it also detects for thermal overload. Now, the reason why we have this RC network here at the input is because the AC waveform signal going positive and negative as it's going playing music program content, down in the low bass registers, like, you know, the 3 to 20 hertz range for instance, that can look like DC to the detector, which will then false trip the circuit. That's why there's a slight little RC charge delay constant employed here, so that the sine wave is not going to false trigger the circuit. And as it's not going to be a constant, you know, straight line of 20 hertz, it's going to be, you know, moving up and down at 20 cycles per second. Well, that gives that enough time for the capacitor to charge and then discharge in the opposite direction. And that's also another reason why this is a bipolar capacitor, because if this was not a bipolar capacitor, if a negative DC or even a negative AC waveform was to charge this capacitor, it'd be charging it in the reverse polarity as it would be if it was a positive going sine wave or positive DC, which means the capacitor would not last very long and eventually you would destroy it. So with all this waffle, what am I intending to do? I'm intending to design a circuit board which employs this DC and thermal protection circuit plus you know, the high current supply lines for a power amplifier. And I'm planning on using to power the ETI 480 power amp modules. That was my initial plan. Although this circuit was already designed as a circuit board about 6 months ago with a high current power supply on it, I just never got around to doing anything with it. But now I am. So I'm kind of working on a new project. So this is my messy breadboard layout of the DC protector. Ignore this LED and transistor here. That doesn't do anything. I was messing around with another circuit yesterday and blew up 2 LEDs in the process and gave up on that idea. I was trying to make a little LED flashing unit so that it could flash the protect LED rather than having a solid on colour on all the time, if that makes sense. It didn't work. So you can buy flashing LEDs anyway, so I might just stick to that original plan. So what I've got here is I've got my power supply set at 12 volts and I'm going to turn the supply on. And there goes the relay. And that was flashing to say it was in protect mode. That's a bi-colour flashing LED. It's blue and red at roughly half a cycle per second of alternate flash. And a solid blue LED here just indicating it's powered to the circuit. This red wire, that resistor doesn't do anything. This red wire is my DC detection in, or the amplifier's input. And this is the positive rail here. So if I touch the positive rail, and then it resets, it instantly dropped the relay out, and I'm not sure of how long the delay was before it detected the DC before the relay dropped out. But they'll put a caption down the bottom of the screen now after I count the frames. Now there's just one problem with this circuit. Now because this is running on a single-ended supply, it's only a positive and a ground, well, if I touch the negative rail, nothing happens. That's because the circuitry, the detect circuitry, which is just basically these 3 transistors here form a passive diode network. It requires a bipolar power supply with reference to its negative. So this would actually be driven off of the AC of the transformer via the full wave rectifier and the center tap, and the center tap is the ground. So therefore the ground of the circuit, which is the negative, is also the ground of the amplifier. So you've got the positive voltage rail and the negative voltage rail plus ground. So this circuit then becomes floating between the two. And the way to simulate that is I will just take a regular 9 volt DC plug pack adapter, and I've got a lead here on the negative side. Now this tip is positive, I believe. Well, it should be anyway. So I'll stick the negative going side lead into the positive potential, and now this is going to be on the negative. So now what it's going to be doing is detecting basically a negative voltage potential, and the relay drops out. If I reverse the connections around so that positive is going in where it should do, it drops out. So I know that circuit is actually functioning. But what I want to know is, what is the minimum voltage potential that has to go through into the DC detector section before the relay will drop out? So I need another power supply that's variable. Alright, I've got another power supply that's variable hooked up across the input in the same polarity as the circuit here. It doesn't really matter, it could be the other way around. Got a multimeter here measuring across the supply input with the power supply set at 0 volts. I'm going to start slowly winding the voltage up until the relay drops out. So we're currently at half a volt. So if there was a half a volt DC offset on your amplifier, well, good luck to your speakers, but the protector won't operate. Winding up to near a volt. We're over a volt now. 1.2, 1.3, 1.4. Whoa, that shot up quick. 1.5. And the relay turned on at roughly 2 volt. So kill the load so that the circuit can reset. seems to be a slight issue with my rotary control, but looks like about the 1.7 volt range. Still not tripping again. I'm just wondering if it's like about 1.8. Turn the load off. Circuit resets. Nope, it's not 1.8, it must be 2 volt. So I'll just set the supply at 2 volts. Yeah, it took a while, but it did detect. So at 2 volt it took probably a good second and a half to actually detect it, because of the charge constant of the circuit. Plus this is a 100 microfarad capacitor, not a 47. It would be a lot quicker if it wasn't. So at 2 volts, yeah, it takes a while to detect, but don't forget, we're more interested in seeing the full supply line voltage at the output. That's what really matters. So I'll wind the supply up to 2.5 and see if it's any quicker at detecting, if I can get the thing to set properly. A little bit. Okay, so I will change it to about 3.5 volts. It's a little bit quicker. So if I go to around 5 volts DC, it's almost instant. So the input sensitivity of this circuit is around 2 volt. That's all I need to know. So I'll just reverse the polarity and see if there's any difference. No, it's the same. So the circuit is functioning how it should. So the next thing I want to do is I want to actually see what the minimum operating voltage of this circuit is. This relay is a 12 volt relay, which is just out of screen there. But these usually operate around about 8-9 volts. Because I'm just concerned with my shunt regulator that I'm going to be using. If I used a 12 volt Zener diode, whether there'd still be, you know, enough available power or voltage to make the circuit operate. So I'm going to wind the supply down. We're at 9 volt. Just until the point where the relay no longer operates. 8 volt. Man, that's a pretty good relay. Even at 7.5 it's still operating. There goes the relay. Around about 7 volts the relay drops out. But the LED doesn't flash either. Oh, it is, but it's just not enough current. So it's lost a little bit of brightness, plus it's bright light in here. So, okay, so what is the voltage across the relay currently? 0.8 of a volt. Okay, so I'll wind up the supply again. Now there's a difference between maintaining voltage and pull-in voltage. So the maintaining voltage is around about 8 volts, but the pull-in voltage will be higher. So I'm currently at 8 volt, and I believe the relay has engaged. So whilst I was talking I wasn't paying attention. Right, so there's the LED flashing. We're at 7 volt. Although I didn't hear it mechanically click, so 8 volts, the LED goes off. 9 odd volts, 9.4 on the supply, 9.18 across the relay. So the maintaining voltage is 8, pulling is 9. So I know as long as the supply doesn't go under 10 volts, the circuit should still operate. Does the DC detector still work? Yes, but it's just a little bit slower. Yeah, see, there was a bit of a difference between the LED going out and the relay pulling in. It's like 4 seconds before the relay pulled in after the LED extinguished. So, if I go to 11 volts now, that's a bit more like it. So I know as long as the supply doesn't go under 11 volts, 12.2 would be good, the circuit will still function fine. So that just gives me, you know, a good indication of what that Zener diode should be, because when the regulator circuit or the shunt regulator circuit is loaded, the voltage is going to drop slightly, so a 13 volt Zener probably would be a better idea. That just gives it a little bit more headroom, even though technically it should be 12 volts. And I've been playing with this circuit for hours. So, yeah, that's the plan. I'm going to have a circuit board manufactured and make it available as a shared project on PCBWay, so if anyone wants a good power supply with a DC protector circuit for a stereo amplifier, even a single channel amplifier, bridged, whatever, then this will be made available for purchasing PCBs for. But that's not the end of the video. No, there's a couple of things I want to test more. Is that Zener diode combination for the back EMF diode of the relay, just to make sure that that functions, and also test the voltage drop of a 13 volt Zener and transistor combination once I get some BD139s in. So that's all coming up in this video. I'm going to try and keep it as short as possible and not long and boring. So anyway, yeah, moving on with the next bit, which is the back EMF snubbing circuit. I've reconfigured the circuit to use the 24 volt Zener diode in series with the 1N4004, opposite polarity to each other. And I'm going to test the difference in dropout time, I guess, when it detects DC, but that's also dependent on the RC network down here. But turn it on. It still works, so I'll simulate a DC fault. And from my perception, I don't notice any difference, but there'll be a caption down the bottom of the screen saying the amount of milliseconds it took for that to drop out. I don't have a 47 microfarad bipolar capacitor to put here, but I do have a 47 microfarad electrolytic polarized, so because I'm only testing positive going DC in these tests anyway, I'll just simply swap that out for a 47 microfarad polarized capacitor and see what the difference in detect dropout time is. Capacitor is changed. This capacitor is going to be used for the filter capacitor in the series pass regulator part of the circuit, but for testing purposes for the input detection circuitry, I'm just going to temporarily put that in there. Turn it on. Everything's still working. Now let's see what the difference is. That was much quicker. So I don't know how many milliseconds that was. There'll be a caption at the bottom of the screen. Now, before I go any further, what I'm going to do is I'm going to take this diode back out of circuit and test it with the 47 microfarad capacitor to see if the speed is any different in dropout time. So it's now reconfigured as it was. Okay, here we go. Yeah, I think that was a little bit slower. So I'll just reconfigure the circuit again to have the Zener back in the circuit. Like so. I've lost my lead. There it is. Okay, I hope you guys are enjoying this video. It's always fun to experiment with something you not really looked into when you actually put the thing together years ago, and then you like investigating the circuit later. Yeah, so I don't know if it was any quicker. From my perception, it doesn't appear to be. I think with just the normal diode as configured as a flyback diode across the relay, conventional, is a little bit slower. So, and as I said, Rod Elliott from Elliott Sound Products has already tested this sort of stuff, so he would know. And he's already done the measurements. He said with a 24 volt Zener and just a normal rectifier diode in this configuration, across the 12 volt relay coil will give you a back EMF of double the supply voltage going into the relay. So for the 12 volt relay it's going to be 24 volt. And I think he said he managed to get the relay to drop out within like 2 milliseconds or something like that. Alright, I'm ready to test this series pass regulator circuit. This is the full wave rectifier. I've just got the positive lead going into one of the diodes. It will still work. This is a TRP41C, which is the only transistor I had to hand. And it has a collector to emitter voltage of 100 volts DC, so that's fine. The pinouts is different to the BD139. This goes base collector emitter, whereas it's reversed on the BD139, it's emitter collector base. But multimeter is connected to the emitter. Power supply is hooked up to, well, the input and ground. So I've got 12 volt Zener in here. I'm just going to see what voltage we get on the output. About 11.45, which is okay, not bad. I wanted to do this test on DC first before I hook it up to a mains transformer, which is 25025, just to make sure that the circuit was wired correctly. Because what I want to do is I want to do a couple of tests on the circuit, like a ripple test, because this transistor will start to heat up quite significantly, hence it's on a heatsink. Not because of the current it's drawing, but mainly because of the ripple it's actually handling. So this value of capacitor may have to increase. The reason I've only got a 47 microfarad in here is because I wanted to try and get it as close to an instant off for the rest of the circuit as possible. There are other ways of doing this, of course, but I chose to do it this way. So I guess now I would have to hook it up to a transformer, and I'm going to put it through a dim bulb just to make sure that nothing is faulty. So we would have like 35 DC volts DC across this capacitor in the end, and it's going to be regulating it down to roughly 12 volt. But we'll soon see. Alright, got the transformer cobbled in. If you don't know what you're doing, don't try this at home. Yep, 11.5 volt. Now I'll just leave that run for a minute. We'll see how hot that heatsink gets just dealing with the ripple. That seems fine. That seems fine. We should have 25 volts. Well, after rectification, yeah, 38 volt, that's about right. So 38 going in and 11.6 coming out. Doesn't appear to be getting that hot. Okay. Alright, how the circuit board is connected. Well, the circuit's connected. It seems fine. Oops, I forgot to connect the relay. That might help. Let's try that again. No, still functions, not much of a drop. Yep, seems to work fine. It's getting mildly warm. Alright, so what I need to do now is measure the ripple across that capacitor. Alright, I've got the scope hooked up to the rectified output of the 4-wave rectifier on a ×10 probe, hooked up to channel 2 of my oscilloscope, which is the blue trace. The input is AC coupled, so this is a little bit of DC there. It's going to shoot off the screen, and there it comes back there, and that is our ripple. I've also got the channel configured to ×10 mode, so we're looking at around about 300 odd millivolt of ripple current there, or voltage. So it's not like very clean, but it's a lot better than what the ripple would be if there was no capacitor there. You would see more like close to the DC supply rail, which is around 36 volt. So to have 300 odd millivolt of ripple, it's okay for a circuit like this. It's not powering an amplifier or anything, so the noise that the ripple is going to be introducing onto the circuit is not going to be terribly significant. However, I will now measure what the ripple is on the output. So that means I have to move from there to across this output there. Oh, man, that stunk. Alright, let me well, in the case of this, I can't see much, so I'll change to ×1 because ×10 is obviously too high. There we go. And according to this, it's actually worse on the output than it is on the input. We're looking more like 500 millivolts roughly of ripple voltage on the output. So yeah, it's not perfect, but it will get the job done. Okay, so I have now tested that fully. I don't need to test that on AC anymore. It powers the circuit just fine. Next step would be to actually have the PCB manufactured and actually build the thing. Yeah, okay, so let me just take you through the final design of the PCB on the computer. Before I do that, I just want to make a correction. I forgot that my oscilloscope was in ×10 display mode, so that would make it more like 50 millivolt ripple current on the output of the regulator as compared to its input of 300. So yeah, its ripple is a lot better on its output, not perfect. So that means that this transistor is going to be handling about 300 millivolts worth of ripple current across its base and collector junctions, and so that will cause that to get slightly warm under normal operation. But other than that, it works great. Right, let's have a look at the CAD drawing. Alright, and here's the 3D view of the PCB, and for a long time this was the graphical image that was used for my intro's background image. So that just goes to show you how long this board's actually been designed in existence. However, it's changed since it was used as a background image. Anyway, here's our large filter bank capacitors here. One of these board mounted rectifiers, which is a 600 volt 10 amp bridge. So I expect that this should be able to handle a current of up to at least 6 amps quite continuously. The AC input comes in over here. This is all the detector circuitry down here. And here are VCC outputs, which I might change to VCC and VEE respectively. So there's 2 positives, 2 negatives, a ground, and another JST connector up here for DC out for positive and negative to go off to, say, a preamp board with its own built-in regulators. So there's no regulation circuitry on this board to drop the higher voltage supply rails down to what a preamp can use. So whatever's connected to this socket here has to handle that on its own board. Going to have a PCB mounted heatsink. I might change this BD139 to the 41C. May or may not do yet, I don't know. The BD139 seems to work for most purposes. But yeah, that's basically the whole entire layout. There's not much really to see here. That's the thickness of our copper traces there. They're 3mm. I'm still trying to work out whether or not I'd have them as bare copper, like tin copper, so it actually can handle a little bit more current or not. That'll come down to my final thoughts before I actually have the board manufactured, and I marked it revision B because yeah, it has been revised since I actually designed it, even though revision A does not exist as a circuit board yet. So and then of course you've got your right in, right speaker, left in, left speaker connections down here, and they're all spade terminals. It makes connecting up and to the amplifier pretty quick and easy, just using spade terminals, 6 and 6.3mm. So yeah, that's a look at the circuit board. We'll just look at the original thing in the PCB editor. As we can see, we've got a nice large copper ground plane here. That goes off for the detector circuitry right round the board. It comes back here. Originally I did have the ground for the LED, power LED here, connected to here. But then I thought about it, that means, because that was connected there as well, that's doing a complete circle back to the center tap of the transformer, which is kind of bad. It should return to the center tap of the transformer, but not like come off of it and then return to it, if you know what I mean. That would cause a nasty earth loop. I'm not sure if I'm going to still leave the ground connected this way from here, or actually connect it from this point to the power LED into the circuit up this way. So it's away from the filter caps, it's coming directly off the center tap of the transformer. I think that might work better. I don't know. So I'd have to like really think about that before I have the PCB manufactured. Because what I do not want to do is I do not want to introduce mains hum onto the high powered side because of all this low voltage DC circuitry and the ripple that's experienced across this capacitor here. So there's some things to think about. But for now I'm going to leave the video here because it's going on up to 40 minutes now. So I'm going to split this up into 2 parts. The second part will be dealing with the PCB assembly and yeah, the final testing. So I hope you guys enjoyed this video. If you did, please remember to go down below and rate, comment and subscribe if you haven't done so already. Anyway, as always, this is Yastro3 saying, see ya, have a great day.